After that, we need to discuss about the capillary effect, which is a very simple phenomena. Okay, certain things you need to understand when you are discussing the capillary effect. The first thing is that if you place, let's suppose this is the container of any particular, and we have placed a certain amount of water in that, and then we have inserted a tube here to check it whether it is rise or not rise. We are not discussing right now on that. It will give you a certain type of shape, like it depends upon the type of the liquid as well. Let's suppose we have two types of condition. Okay, one is that if the intermolecular forces are dominant, it will create a shape like this. Okay, and if the molecular and wall forces are very strong, the liquid will give you a such type of shape. Okay, and we can say that this shape is like concave shape, and this is convex. And this appearance of the shape is so called as meniscus. Second thing which we need to know is, let's suppose they rise or may not rise in that way, but I'm making this figure in just editing it. Okay, this is the meniscus shape of normal water. Okay, and this is the meniscus shape of mercury, Hg. So we define a term as a contact angle. The contact angle is nothing, we just tangentially draw a line with the molecular touch and how they interact with this wall. Okay, so it is for water will be like this. Okay, and this will be its theta, and for a particular liquid might be it's definitely, if we draw a line tangential to the molecules of these molecular present at the very solid near to the very solid wall, will be like this, and this is its angle, which is so called as, these both are, we can say that, contact angle. Now, why these type of forces, these type of shapes appears by the liquid, is just because of the intermolecular force dominancy, or the surface or solid surface and liquid molecule force dominancy. Like we see that water is so called as the wetting material, so this is the wetting fluid. Why? Because it's has an attractional with the solid wall a lot. On the other hand, if we see the mercury, which won't have any wetting, we can say that unwetting property, unwetting fluid. Why? Because it won't attach with the solid wall. It's always try to bind with its own molecule. Okay, these are simple, some of the terms which I describe and which are associated with the capillary effect. Let's suppose we have two containers and we have different fluid, like one we have mercury, one we have water. We have placed certain level here. Again, for water we have maintained a certain level here. Then we have inserted a tube here with certain diameter. Similarly, the same diameter, the tube is inserted in this container as well. As we know that this is unwetting property, its angle is we have find was greater than 90. This theta is definitely greater than 90 degrees with unwetting property. On the other hand, if we see water, will give you the angle something very less than, almost equals to water, give angle of 0 degrees even. Okay, so this this angle, this contact angle will be around less than 90 degrees. Okay, and it has wetting property as well. So you will get the maximum capillary rise here for this fluid, okay, for that particular range. On the other hand, if we talk about the mercury, it won't rise, actually it decrease its length in that capillary tube. So now we need to mathematically express all these things. So you can see here, when it rises from this level to that level, let's say it rises with a height of h. And the contact angle here, let's say it is phi. The weight of whole this liquid acting downward, and at the circumference of the tube, it is only the surface tension which is holding it for that particular height. So this is the force which has this direction, although if we resolve it in two components, like one will be this component and the second will be this component. This is theta, so it is your horizontal component, which we so called as, if we saying this is Fs, so it will be Fs cos phi, and it will be Fs sin phi, which is not balancing the weight. Actually only Fs cos theta, which is acting upward in this particular direction, is responsible to balance the weight of this liquid. So we can say that Fs will be equals to 2 pi, and it is acting along the radius, along the circumference, 2 pi r surface tension and cos theta. On the other hand, the weight will be equals to a specific weight multiplied by the volume, and we know that the volume of this complete cylinder will be 2 pi r h, pi r square h, sorry. And so the specific weight is equals to rho g. So the equation becomes rho g multiplied by pi r square h, and we have to equate both these things. 2 pi r cos theta will be equals to rho g pi r square h. So pi will be cancelled out, the power will be reduced, and we have a formula for height. If we determine how much capillary rise will appear for a particular case, what we need to know is twice of surface tension cos theta and divided by rho g. So this is the simplified relation you will get by mathematical expression, which shows that if the surface tension is higher, the capillary rise will be higher. If cos theta value is higher, and it is only be higher if the theta tends move its value towards the 0, and if it will move beyond the 90 degrees, the value will be reduces. So if we move beyond the 90 degrees, which show that the capillary rise won't occur, although the reverts like the liquid move down in the tube will occur in these cases. Okay. Then we have, I just show you that what is cohesive forces, what are the adhesive forces, concave meniscus and convex meniscus for mercury. And we have derived these equations as well. One more thing is that meniscus describe whether the capillary rise will occur or not. Then we have a numerical, and it's a very simple numerical. The pressure are sometimes determined by, like in barometer, what happened, the column height is representing how much the atmospheric pressure for that particular surrounding. So similarly, the height definitely represent the pressure of particular condition. What we need to determine is the diameter of a cleaning glass tube is required so that to rise a 20 degree centigrade capillary action with a height of this. Okay, they show us the height as well, and in the second part they also tell us to determine the trend of capillary rise, that how the diameter of the tube and capillary rise has their own trend. Like if we are reducing or increasing the diameter, how the height of the column vary. Okay, so simply what we have in our data, we know the surface tension from the table. We have they have given us the density of water, okay, for this condition, and the height. Okay, and we know that the angle is 0 for water at 20 degrees centigrade. We use this relation, and in which we have to determine the radius. So we will rearrange it in that manner, and we will put all these things in a formula. So we will get this result that R value is like this. But we are dealing with the diameter, so we just need to multiply it with the 2, multiply by 2 the value of the radius. In the second part, what I have done is only I use the previous relation, okay, the upper relation, sorry, the lower relation, second one, and in which I am varying the value of H, and I'm getting different value of R, because the value of surface tension is constant, the value of theta is constant, and value of rho and G both are constant. So I have arranged the height in a manner that 0.1 mm to 2 mm. What will be the trend we will get? Okay, then definitely this formula we all putting the values in SI system. So I reduce the height unit into from mm to meters, and respectively I am getting the values in meters for diameter here from 0.1 mm to 2 mm respectively. Then I reduce it in mm. Definitely I want to know the trend in mm for both height and as well as for diameter, and we come to across with this type of trend that if the height is reducing, we're showing that the diameter of the tube is much higher, and if we are reducing the diameter, the column height is increasing and increasing, and you are getting this type of trend for different types of diameter and how it changes its height. So the last numerical for this is very simple. In fact, there is a person who carried out a practical, okay, or an experiment, and he find different values. Definitely these are the very precise value of theta, which you are saying that for water theta is equals to 0, and the capillary height is that much, and the surface tension is that much. It's all depends upon the purity of the water as well. On the other hand, if we are talking about the meniscus or contact angle of the liquid with the solid surface, it definitely depends upon the cleanliness of the surface of the glass as well, or the material whatever we are using. So he took the experiment so rigorously. For that he got some results. So firstly, what we have to do is we can plot these values, and we can see what happened, which type of trends we are getting. So okay, when I have plotted this value, so how I can plot it? We know that the formula of capillary effect is H is equals to twice of surface tension cos phi over specific weight, or you can say rho g, and r, the radius of the capillary rise. If I'm talking about that the equation of a simple straight line is y is equals to mx plus b, and I'm reducing it in the form of this equation. So S will be equals to twice of surface tension cos theta, all these values are constant, over rho and g is constant, 1 over r is varying, plus 0. So we will get this these values. So what I have to do is I have to plot h against 1 over r in order to get a straight line. So I solve it in that manner in the Excel sheet, because I have various values. And I get different results. So one thing, these are the values given in the data, the diameter and the height. Okay, I reduce it in the form of meters, and then I reduce it in the form of radius, and I have to plot 1 over r of the 1 over r. Okay, so I find these values respectively. On the other hand, for height I just need to convert it from inch to meters. All values are converted into meters in this column. Okay, so when I plot it, I will get a very straight line, and then I find the relation of y is equals to 1.3 exponent minus 5x. This is the expression of this straight line, which I find using Excel, which is equals to y is equals to 1.3 exponent minus 3 minus 5 with x, with no y-intercept. Okay, y-intercept is again 0. So this is y, which is equals to h, this is x, which is equals to 1 over r, although the rest of the values can be equated into this factor, and the other value all are equals to 2 is surface tension cos phi over rho g, which is equals to 1.3 into 10 to the power minus 5. So what we have to do in the first case? In the first case, we have to fit the curve of these data and estimate the value of the product of surface tension and cos theta. So we can find here, they have given us the value of G is 9.81, value of density is 998 point. The value of density, you can take it as 1000. You can take here as 1000 kg per cubic meter. If you put these values in this formula, you will get the product of surface tension and cos theta. Okay, like 1.3 into 10 cube power minus 5 is multiplied by 1000 multiplied by 9.81 and divided by 2 is equals to 0.0637. So surface tension and cos phi is equals to 0.0637. This is the first part. The second and third part are so simple and you need to solve by yourself. Once you have find these two values, what you need to do is if it is assumed that the surface tension is equals to this value, what will be the value for theta? So in this relation which we have find here, you will put the value of surface tension and you will get respective theta. And in the second part, again what you will do is you put the value of theta and respectively you will get the result of surface tension. From now the second chapter is started. So